Hello, viewer. Z. Hola. I did ask about JoJo's last period. I was trying to understand the JoJo memes. And I was told that you're an expert and maybe you can explain it to me during the Zoom classroom. You can be the teacher once my lesson is over, okay? Hi, little boy Bugs. Come here. Oh, little boy Bugs, you're so good. Little boy Bugs. Little boy Bugs. Can I get a num num? Oh, thank you so much. Can I get another num num? Thank you. Can I get another num num? One more. Num num. Num num. Num num. Bugger. I want a num num. Thank you. Good boy. Okay, I better start teaching now. Bye-bye. Hazel. Oh. What do you do? What do you do? Oh. She do. Okay. I guess I better get started. You want to take that back that Hazel is just chilling? Because she was not chill. Okay. Hello, everyone. So we're done with gravitation for right now. And we are going to start talking about rotational dynamics. So the first thing I'm going to talk about today is torque. Okay, so what is torque? Torque is a twisting force. Okay, so I don't mean to say that it's a force, but it quantifies the amount of twist. Okay, a force is quantifying the amount of push. A torque is quantifying the amount of twist. Okay, so what we want to have sort of in our heads is imagine a blob, and this blob has a pivot point. So this is a pivot point. Okay, and there's a force acting somewhere. So if something is rotating, then where the force acts is important. So if I think about holding this calculator, I'm going to apply a force in the same direction. If I apply that force here, it rotates one way. But if I apply the same force down low, it rotates in a different direction. Okay? So the way that it rotates, even though I'm exerting the same force, the way that it rotates depends on where I push. Okay? It also depends, how quickly it rotates also depends on how far away from the pivot I push. Okay? So we got a force that's acting right here, and there's a vector that extends from the pivot point to where that force is applied. I will call that vector R. All right. And the definition of torque is denoted by the Greek letter tau, is the cross product of R and F. So this is the real definition of torque, okay? And we are not going to have much occasion to use this definition of torque at this level, okay? If you wanted to be a mechanical engineer, for example, where you have a structure that has multiple forces acting on it in all different directions, and it's a three-dimensional structure, then using this formula for torque becomes essential. But most of the time, it's not necessary. So, and I'll get to that in a second. So, the units of torque are obvious from this equation because it's a distance, a position vector, times a force, okay? So it's newtons times meters, force times distance, okay? So I want to remind you about the magnitude of the torque. So the magnitude of the torque, which I'll just denote by tau without the arrow over the top, is R cross F, the magnitude of R cross F. And if you recall, magnitude means magnitude of the first vector times magnitude of the second vector times the sine of the angle between them. That is the magnitude of a cross product, okay? When I say sine of the angle between them, we have to be a little bit careful here, because when we do sine of the angle between them, so let's say I have two vectors, R and F. You need to shift the vectors so that they start at the same location, and then that is the angle between them, okay? So here you might be tempted based on this picture to call the angle between them whatever that angle is. But what you have to do is you have to shift this vector over so that it starts at the same position, and then take the angle between them like that. So that would actually be the angle between them. All right, so you got to be a little bit careful about that. So if we think about this force, I can break it up into components. Okay, this component right here is parallel to the position. Okay, so there's a really good question in the chat, which is, does the force also accelerate the entire blob or just rotate it? And the answer is it depends. So I am assuming in this class that the pivot point is actually holding it in place. So basically the force, the applied force, is rotating the thing. And if it were just a thing in outer space and you pushed it, it would actually translate and rotate in response to that. But because you have the pivot it's being held in place at the pivot point, so it can only rotate. All right. So it's a matter of, is it something that is held in place by a pivot, or is it actually just free floating, in which case it can rotate and translate. Okay. So here we have a force. There's a component of the force parallel to the position, and there's a component of the force that is perpendicular to the position vector. And we can see that the component that is perpendicular is opposite the angle. So the perpendicular component is F sine of theta. So you can see that right here we have F sine of theta. So that means that torque, the magnitude of the torque vector, is actually F perpendicular, the perpendicular component of F to the radius vector, times R. So this is actually kind of our preferred formula for torque in this class. And this is the formula you would want to use if you have rotation about a single axis. Okay? If you think about something that is truly three-dimensional, it can actually rotate about three independent axes. Like a calculator, it can rotate like this. That would be an axis of rotation like so. It can have an axis of rotation like this, which would be rotating like this. Or it could have an axis of rotation that is up and down, which is rotating like this. So if we have a single rotation about a single axis, so we just pick one of those three and it rotates, then you only need to use this formula. So this is what we're going to be using in this class. If the force is going to tend to rotate the thing in the counterclockwise sense, that is considered a positive torque. And if it would tend to rotate in the clockwise sense, that is considered a negative torque. Okay? And the net torque is just going to be the sum of the individual torques that are acting on the object. Okay? Now, because we're rotating about a single axis, torque is basically a scalar in this case. But if you have a fully three-dimensional object that can rotate about three independent axes, this would be a vector sum. Okay? But if you have rotation about a single axis, then torque is basically a scalar. It has no direction. So what about this force right here? What do you think? Type it into the chat if you think it's a positive torque or a negative torque. I'll wait. Okay. Get my example set up. Excellent. Yeah, it's a positive torque. Why? Because if this calculator is the blob, here's the pivot point right here, and I apply a force kind of in this direction, you can see applying that force made it rotate counterclockwise. So that's a positive torque. All right. So I have a blob here, and this blob has three forces acting on it. There's a force acting right here. This force, I'm going to call that force 1, has a size of 100 newtons. And the angle shown, this angle right here, is 40 degrees. All right? There is a second force acting right here. It points in this direction. It's a 70 Newton force. And this angle is 60 degrees. Okay. And then there's a force acting down here in this direction. All right. And it is a 500 Newton force. And it is this angle right here is 30 degrees. Okay. Now I need to give, in order to calculate torque, you need to know the distance from the pivot. So let me give the distances from the pivot for each of these forces. This distance right here is 0.7 meters. This distance right here is 0.3 meters. And this distance right here is 0.4 meters. Okay. All right, and so what we want to know is what is the net torque on this object as a result of these three forces. So there are three forces. There are three forces, and so therefore the net torque is going to be tau 1 plus tau 2 plus tau 3. All right, and now let's figure out what are the signs of each of these three. Well, if I let this calculator represent the blob, here's the pivot, kind of like right here. All right, and the first force is acting sort of diagonally in this direction to the right of the pivot, so that causes it to rotate counterclockwise. So the first one is going to be positive. And I'm just leaving an open parentheses just for, because I'm going to fill that in with the F perp times R. Now for this second force, here's the pivot. The force is acting up above the pivot. So, and it's acting kind of in this direction. So I push like that, and it rotates again counterclockwise. So the second torque is also positive. The third force is acting below the pivot. So if this is the pivot and it's acting kind of down in this direction, so if I do that, I can see that it starts to rotate in this sense, which is the clockwise direction. So that is a negative torque. All right. So now we got to figure out what is the perpendicular component of each one. All right. So if I look right here, for this first force, here's the line connecting the pivot to where the force is applied. So F perp refers to the component of the force perpendicular to this line that connects the pivot to where the force is applied. Okay. So this line connecting the pivot to where the force is applied is horizontal. So the perpendicular component is vertical. So this is going to be F perp for that force. Forces that are applied at different locations have a different definition of what F perp is. Okay. So this is adjacent to the angle shown. So F perp is going to be 100 cosine of 40 degrees. All right. Now let's go to this force, force number 2. Here, the line connecting the pivot to where the force applied is vertical. So perpendicular to that is horizontal. Okay. So this is F perp. And we can see that it is opposite to the 60-degree angle. So that's going to be a sine function to get F perp. So we have 70 times sine of 60. Now let's look at this one. Again, the line connecting the pivot to where the force is applied is vertical. So perpendicular to that is horizontal. So this would be F perp. And we can see that that is adjacent to the angle that is shown. So that is going to be a cosine. So this is going to be minus 500 cosine of 30 degrees. All right. So now I have to multiply these F perps by their corresponding R's. So for the first force, the R is 0.7. For the second one, the R is 0.4. And for the third one, the R is 0.3. So what does this end up being for our net torque? Well, the first term is 53.6. The second term is 24.2. And the third term is 129.9. So combining all those, gives a net torque of minus 52.1 Newton meters. All right. And so what that means is that as a result of these torques, this thing will rotate in the clockwise sense. All right. Cool. So there's an example of calculating net torque. So our next topic, so we're going to leave torque for a second and then come back to it almost immediately, is the topic that is called center of mass. Okay, so center of mass, if we wanted to explain it just in words, you could think about center of mass as the average location of the mass. Okay. All right. So the center of mass is not necessarily the geometrical center of the object. Okay. If the object is very symmetrical, if its weight distribution is symmetrical, then the center of mass actually will correspond with the geometric center. So, for example, if I have a piece of paper, the mass is evenly distributed across the piece of paper. So the center of mass is actually going to be the geometrical center of the piece of paper. Okay. If you have a dumbbell and each the mass on either side of the dumbbell, those two masses are equal to each other, then the center of mass is going to be actually in the geometrical center of the dumbbell. But what if you had an asymmetrical dumbbell where there's a little mass on this side and there's a big mass on this side? Then that means that it's more skewed. The center of mass is going to be more skewed towards the side where there is more mass. Okay? So it's actually a weighted average. The more massive a particular location is, the closer the center of mass is going to be to that location. The other way that you can find the center of mass is it is the balance point. So if I look at this knife, for example, if I want to find its center of mass, I try to make it balance, and I can see that it balances right about there. So the location of the center of mass is just right where the tang starts. It's basically at the location of that first pin, because that's where If I put my finger there, it balances. Okay. If you take something like an axe, okay, this axe has a wooden handle and it has a metal head. So it's kind of like an asymmetrical dumbbell, right? There's more mass on this side than there is on that side. So the center of mass is going to be skewed to that location. So like if I put this right here, try and find the center of mass, it's like right there, okay? So the center of mass is right about there. Okay, so how do we actually calculate the center of mass? Well, the first thing I'm going to talk about is a discrete mass distribution. Okay, so a discrete mass distribution means that you have, mass number 1, mass number 2, mass number 3, mass number 4, etc. So you have, you can count the individual masses, and you have an origin, which is right here. And each of these masses has its own position vector. Okay? So you have R1, R2, R3, R4. Okay? So in this case, the x-coordinate of the center of mass is going to be m1 times x1 plus m2 times x2 plus m3 times x3 plus ... however many masses there are, divided by the total amount of mass. So this is the definition of the center of mass for a discrete mass distribution. That's the x-coordinate. If you wanted to know the y-coordinate of the center of mass, you would replace the x's with y's. All right. And then similarly with the z component, the z coordinate of the center of mass. All right. So I taught my AP Physics 1 class this last year. I don't know about the IB Physics, but yeah. All right. So now what I would like to do is I would like to talk about what happens if you have a continuum distribution. So we're going to talk about the center of mass for a continuum distribution of mass. Okay, so that's kind of our third topic for today. So if it's a continuum distribution of mass, then that means that we don't have m1, m2, m3, m4, m5. We have a lambda of x. Okay? Remember, lambda is the linear mass density. It's dm dx. Okay? All right? So, all right, so in particular, that means that if I multiply both sides of this equation by dx, that means dm is equal to lambda of x times dx. All right. Okay, so how do we take what's called the continuum limit? So there's something called the continuum limit. Okay, and so this is kind of important. So let's say take for example m tot. The total mass could be thought of as the sum. So I'm using sigma notation for sum of m sub I, the ith mass. You take all the masses and you sum them all up. Now in physics, I know in your math class you might have like I equals something to I equals something. And in physics, the vast majority of the time, you sum over all possible values of I. Okay? And so most of the time in physics, you won't even really you won't even specify what the, I equals, what is that even? It's just understood that you're summing over all of the masses, unless otherwise stated. So I left out the limits on the sum. So if we take the continuum limit, a sum becomes an integral, okay? And then m becomes dm. So it becomes the integral of dm, all right? Now, dm is equal to lambda dx. So the total mass is the integral of lambda dx. That's the total mass of the thing. Okay? So that actually accounts. Okay, so why does it change? Because we're taking the limit as the size of the individual masses goes to 0. So in your calculus class, you might remember that the integral is a limit of a Riemann sum. So what we're doing is we're taking the limit of this sum over masses in the limit that the masses become infinitesimally small. So that becomes an integral over dm. All right? So that handles the denominator in the definition of center of mass. But now we got to handle the numerator. Okay. All right. So handling the numerator. Well, the numerator is the sum of m times x. So mi times xi, and we're doing the sum of that. So in the continuum limit, again, we're taking the limit as the masses get really small. Okay? So mi becomes dm. The sum becomes an integral. And then it's just, dm. And then it's just multiplied by x. So it's the integral of dm times x. Now, of course, dm can always be written as lambda of x dx. So this becomes the integral of lambda of x times x dx. So that is what becomes of this sum of mass times x in the continuum limit. Okay? So if we look at our definition of the center of mass, it's the sum of mi times xi divided by the sum of mi. And so in the continuum limit, this numerator portion becomes this. So the integral of lambda times x dx. And then the denominator becomes the integral of lambda dx. And so this is the continuum definition of the center of mass. It's a ratio of two integrals involving lambda. Okay? All right. So you should be able to calculate the center of mass in the continuum limit. And because this is an integral over x, this is only for like one-dimensional objects, okay? There is a generalization of this formula for, three-dimensional objects, but that involves multivariable calculus, which is not in the scope of this class. So why are we talking about that? Well, there's a torque due to gravity. So if we hold something, why is this calculator, why does it want to rotate like this? It's because I'm holding it, there's a gravitational torque, okay? So there is a gravitational torque. That's what I want to talk about next, is the gravitational torque, which is the torque due to the gravitational force. So what I want to imagine is a beam, okay? And this beam has a pivot point at its left end. And I'm going to imagine chopping the beam up. Okay? I'm going to imagine chopping the beam up. All right? Into a bunch of little pieces. All right? Now, what is the force on each piece? So maybe this is the 1, 2, 3. This is the third piece. It has a downward force acting on it. And this is the third piece, so it has mass m3. And the weight force is m times g, so it would be m3 times g. Now, how far does this force act from the pivot point? It acts a distance, x, we'll call it x3, from the pivot, okay? And because this beam is horizontal, we can see that this angle is 90 degrees. So the force already is perpendicular. So we're not going to worry about the sine or the cosine term. And you can do this similarly for all the parts of the beam. So like here's the end part. It has a mass maybe m sub n time. And then its weight force would be m sub n times g. And it is a distance, that force is acting a distance x sub n away from the pivot, okay? So our total gravitational torque is going to be it's going to be m1g, so that's the gravitational force on this piece, times its distance from the pivot, plus m2g, which would be the mass of this portion, or the force on this portion, times its distance from the pivot point, plus, and we just add that up for all of the different terms, okay? M sub n times g times x sub n. All right? So you can see that every term has g. All right? So I can factor it out. And then what I get is a sum over mi xi. So if we take the continuum limit, what does the sum over mi xi become? It becomes the integral of lambda times x dx. So in the continuum limit, this becomes g times the integral of lambda times x dx. All right? So this is a formula for the gravitational torque. All right? But I'm gonna write this in a slightly different way. That's, I think, a little bit more illuminating. So I'm going to take the formula for the gravitational torque, okay, and I'm going to multiply it by the integral of lambda dx. And I'm also going to divide by the integral of lambda dx. So you can see that I've multiplied and divided by the same thing. So these would just cancel out, and I would get back to my original expression. But if you notice, this is m tot, okay? Because we already set up here that m tot is lambda of x times dx, is that integral is m tot. And then you can see that you have m tot times g. So mass times gravity is the total weight. All right? And then right here, we see the definition of center of mass. So I could also write the torque due to gravity as the perpendicular component of the weight force times the distance between the pivot and the center of mass. So this is a kind of a better expression for the gravitational torque. So the key lesson here is that the gravitational torque acts as if all of that weight were concentrated at the center of mass. Okay? It acts as if all of that weight were concentrated at the center of mass. All right. So let's do an example. I wrote a good example down in last period. So what if we have like a beam, okay, and the beam is pinned at its lowest point, like so, okay. The beam is 3 meters long, and it is making an angle of 50 degrees with the horizontal. Okay, it's making an angle of 50 degrees with the horizontal. This beam has a, okay, so here's the beam. This beam has a lambda of x given by 2x cubed kilograms per meter. And the beam is, as I said, it's 3 meters long. Okay? And so what I want to know is, what is the gravitational torque on this object? Okay? So one of the things we can see is that to calculate the gravitational torque, I basically need to do two integrals. The integral of lambda times x dx and the integral of lambda dx. So let me do both of those integrals. So it's going to involve the integral of lambda dx, which is going to be the integral of 2x cubed dx. And I know that it's a 3 meter long beam. So I'm going to integrate that from 0 to 3. All right? And I'm not going to show the math of that, but it is, that is going to be, let's see. It's going to be 3 to the 4th divided by 2, which is 40.5. All right. So this integral of lambda, okay, this integral of lambda dx is actually the total mass of the beam. All right. So I have that m tot is 40.5 kilograms, which means that the weight of the beam is going to be mass times gravity. It's going to be 405 newtons. All right? So that is the weight of the beam. Now I need to do the integral of lambda times x dx. So it's going to be the integral from 0 to 3. Because I'm multiplying by another factor of x, it's going to be 2x to the 4th dx. And again, I'm not going to show the math on the integral. You can use a calculator, you can use Desmos, you can use Wolfram Alpha, or you can just do it by hand. And this integral is equal to 2 times 3 to the 5th over 5, which is 97.2 kilogram meters. So that actually is going to allow us to figure out what is XCM. All right? XCM is going to be the ratio of the integral of lambda times x, which was 97.2. The integral of lambda times x divided by the integral of just lambda by itself, which I calculated was 40.5. All right, so that means that the center of mass is at 2.4 meters. So the beam is 3 meters long, and the center of mass is 2.4 meters along the beam. Okay? So here's 3 meters. 2.4 is about 2/6 of the way. So the center of mass is like right here, almost at the end. Why is that? Because the mass is more concentrated towards the end. The bigger the x value, the more the mass. The symbol for center of mass is kind of like the BMW logo. So the center of mass is like right there. All right. So that distance is 2.4 meters. Now, and then we have a weight force that is going straight down that is 405 newtons. Okay? Now, this is where the perpendicular part comes in, because we can see that this force, the weight force, is not perpendicular to the beam because the beam is at an angle. If you work out the geometry, this is going to be weight perpendicular. And if you work out the geometry, then this is actually 50 degrees. So we can see that weight perpendicular is adjacent to the angle, which is going to be cosine. So we have 405 cosine of 50, which is 260.3 newtons. So then I can figure out the gravitational torque, which is going to be weight perp times RCM. So that's going to be 260.3 times 2.4. Which is 625 Newton meters. And we can see that gravity is going to cause this beam to rotate in the clockwise sense because it's pinned down here at its base. So that is actually a negative torque. All right. So there you have it. one thing I want to talk about just really briefly is if you have a uniform beam. So if I say uniform means that the lambda is constant. And in that case, it means that the center of mass is actually in the middle. So if I had said this was a uniform beam of mass 40.5 kilograms, then you would have put the center of mass right here, only 1.5 meters up the beam. Okay? So that is my lesson for today, and I will see you